Okay, we're going to take you on a journey, okay, to explain to you how we got into newborn sequencing and what it delivers and where we're going with this, okay? It's very exciting, and this is one of the first public venues we've ever talked about this. So, woo. All right, so first of all, we live at a unique time point in history. It really is. The cost of genome sequencing is plummeting. It's now $380, which is amazing. The speed is also amazing. You can decode a genome and diagnose a baby in 7 hours. And our knowledge of genetic disease is continuing to fill out nicely. There are 7,150 known genetic diseases. This creates amazing new opportunities in pediatrics, where these diseases collectively are the biggest thing. They're the biggest ticket item in terms of any children's hospital. So let's start off with a case, right? And this case was in New England Journal last year. So you might have read it, you might not. I got to take my glasses off so I can read it. Yeah, this is a quick one. I had 2 cases and I picked one of them. This is a beautiful case. This is a cheerleader, 14 years old, and she's having supper, previously healthy, and she feels dizzy. She collapses. Her mum finds she's pulseless, calls the emergency medical services. When they arrive, she's in ventricular fibrillation. They cardiovert her. They start to run through the code routine in terms of medications and cardioversion. She's transferred to a local hospital, and then from there to Rady Children's Hospital, which is, you know, the Boston Children's or the Tufts Floating Hospital of San Diego. She is still having a very stormy course. She can't maintain an adequate blood pressure, and so a decision is made to put her on heart-lung bypass, what we call ECMO, extracorporeal membrane oxygenation. This is a temporizing measure. This does not long-term replace those functions, but the goal is to get to her heart to recover in time before we wean that off, okay? Now, she is positive. Of course, this happened just a few months ago, so she's tested for COVID and for other viruses, and she comes back rhinovirus positive. So the clinical diagnosis is very self-evident. This is a viral myocarditis, and it should be self-limiting, and we'll give her IVIG and some steroid, and she'll be just fine. However, because she's at Rady and because we've been doing lots of newborn genomes, the PICU attending says, let's get a genome cooking on this individual. They do, and 2 days later we have a diagnosis. And in fact, she has a genetic cardiomyopathy. The defective gene is lamin A, which is, that's what's wrong with her, right? So she has heart failure as a result of this genetic cardiomyopathy. So she's listed for transplant that day. She gets transplant later in the week, and she goes home 3 weeks later. This is what's happening in response to those curves I showed you. Girls like this hitherto would have died. They would have been wrongly treated for a myocarditis. Now, she might have had a little bit of viral myocarditis that may have prompted this or triggered this going from asymptomatic to fulminant. But nevertheless, that was not the underpinning cause, and treatment with IVIG would have resulted in a bad outcome here. And people wouldn't have realized it until it was too late, and then they would have searched for a genetic cause, and by then she would have been ineligible for transplant. So over the last decade, believe it or not, that's what I've been focusing on across a couple of organizations for the last 6 years at Rady Children's Hospital, where we are mass producing answers for critically ill kids like this. And you can see there that the statistics, we're targeting this at 2% of kids who are in intensive care units. We get them a genome as fast as humanly possible. And the goal is to alleviate that bottleneck A, which has been a huge problem hitherto. Really, genome decoding, whether it was an exome or a genome, previously was way too slow to be relevant to intensive care unit management. And these diseases are probably the leading cause of death in such children. So since we started this, which was 2011, we've had multiple research studies confirm that 1 in 3 children will get the diagnosis, 1 in 4 will have a change in management, 1 in 5 will have improved outcomes, and those are staggering numbers. And that's before we have this new era, impending era of gene therapies. So we're now starting to see this be implemented as standard of care, and it's predicated partly on studies such as this one. This is an implementation study, not research, not implementation, in this case in Medicaid in California, which is called Medi-Cal. So 178 babies at 5 children's hospitals got what I just showed you, and the results recapitulated in the real world, in the Medicaid population, what the research studies had shown, which is not always the case. Research does not always translate into the real world. Furthermore, surprisingly, this technology saves healthcare dollars. And so, as you can see, net, there were $2.5 million in net savings as a result of 178 babies getting this technology, despite the fact that it's relatively expensive. And those cost savings, as you can see on the left, they erode very rapidly if you don't have a rapid result. And then there are ongoing savings in addition to the first hospitalization, and we don't yet really know how big that is because these kids still need to grow up. So what that's led to is that now across the United States, we're seeing Medicaid programs embrace this and cover it. We have 4 states currently who have coverage policies, and we have 1 major payer, which is Anthem Blue Cross Blue Shield. Triumph! Awesome! The job is done. I can retire and go drink sweet drinks with, one of those umbrella thingies in them. No, not quite. So we've eradicated bottleneck A. It's still going to take a few years to trickle across. We still need to upskill the physicians and the nurses and the genetic counselors. But we have another issue, one which many of you who are in drug development are very aware, which is that doctors don't necessarily know what the current treatment regimen is for a rare or ultra-rare disease. Chances are they've never seen it before, never treated it before, and they're reliant upon sub and super specialists to actually tell them. And for many of the treatments, actually, they didn't go through clinical trials. It's a matter of case reports and small cohorts that have guided the evolution of management for these conditions. So we found this second problem, which was the therapeutic odyssey. We return what we think is a life-saving diagnosis, and we don't actually see that benefit. And this is how we got into newborn screening, and I'll show you how. So the first thing that we did then was to work with a number of companies, some of whom are here, Rancho Biosciences, EPAM, Genomenon, to build out a system, and also with Alexion Pharmaceuticals and Sebastien Lefebvre. Is he here? Oh, Seb, that was your moment of fame. Oh, well. Tom, I did it, okay. To build out this amazing system where we integrate that information across thousands of interventions for hundreds of diseases. And this is now live. It's called Genome-to-Treatment. And so currently it covers 421 conditions and 1527 different interventions for those conditions. And that's the website. We're continuing to build this out, but having built this, we had an aha moment. Now remember, this is for critically ill children in intensive care units who are newly diagnosed with a genetic disease. So these are severe genetic diseases, childhood onset, that have effective therapies. Where else do we use that? How about newborn screening? So that's what we decided to do. We pivoted. And what's the rationale here? What we have realized is a diagnostic modality is wonderful, but we're waiting until the kids are in an intensive care unit. And furthermore, not every child is getting that test. Maybe 1% currently of the kids who need it are getting tested. And so how do we close that gap? And to close the gap, we decided, how about a universal delivery system so that every baby could benefit from the same technology the way they currently do? Every baby gets a heel prick test within the first 24 hours after delivery, and they're tested for roughly 30 genetic conditions. What if we could take that up to 500 or 1,000? What if we could do it for every genetic disorder for which there's effective therapy? And this just shows you that curve again. And then the two lines that are flat are newborn screening. So it's gone from 27 to 32 conditions across the same time period, and the number of lives affected has gone from 6,400 to 6,800 in that period. So we want to do that hockey stick thing there and immediately jump that to 400 or 500 and see how high we can get the number of affected children to benefit. So let me show you where it's at. So the first thing was we had to take the GTRX resource and the same companies, Rancho, Alexion, and rebuild that out so that we were qualifying these conditions for newborn screening, which is really strict. The criteria were established in 1968 by the World Health Organization, and they're shown there. We've listed them 1 through 6. Doesn't quite fit the slide. That's okay. You can read most of them. And so we put them through that. And as you can see in phase 6, currently 14% have been rejected, 65% have been retained as Group A, which means there aren't too many gaps in our knowledge. We're pretty confident these ought to be tested. And then a 21% in a Group B, which means we're going to do clinical studies and validate that these are really worthy of newborn screening. You with me so far? Good. Okay, top line A is what we've done for the last decade. It's diagnostic rapid whole genome sequencing. It happens in about 3 days, 3 to 5 days. As you can see, we screen for 7,200 disorders. We look at 10 to 20 variants per patient. It's phenotype informed. These are babies and children in intensive care units. And in about 1 in 3, we issue a diagnostic report. And this marvelous new virtual acute management guidance system, GTRX, feeds in then the appropriate therapies that are indicated for that newly diagnosed condition. What is immediately apparent is, gee, if we're going to shift this to newborn screening, it doesn't look terribly different. The big difference is most of the kids for newborn screening are going to be negative, right? Genetic diseases in the general population are quite rare, 1%, maybe 2%, whereas in the NICU setting, 1 in 3 gets a diagnosis. In order to make this work, we needed to scale, we think, to 140 million children worldwide. That's the number of children worldwide who get conventional newborn screening. So basically, first world or high-income countries and middle-income countries almost universally screen at birth for some set of conditions, maybe not as much as in the US, but they potentially, if we can get the form factor right, if it looks like a newborn screen, so a heel prick and a Guthrie card, and if it costs a small enough amount, we could convert 140 million babies worldwide. What do we need? We need a very robust data management system. Now, we had built a data management system using conventional technologies for the diagnostic piece, and we hit the wall, and it's called the N+1 problem. And I'm not going to steal my own thunder because I'm going to come back to that in a future slide. But we had already flunked out. At some point, you have added so many genomes that you hit ping for a query, and you may as well go have coffee and take a vacation, because it's just not going to give you a result that would certainly not scale to the types of numbers that we wanted. So let me just emphasize a couple of the details here because I'm going really fast. So the genome is the same. Right now, it's an Illumina 30 or 40x genome, 2 by 100 nucleotides. It's fast. It's done in 2 or 3 days. We then run that through a pipeline. So we go to variants, standard variant callers. But now what we do instead of interpretation is a database lookup. We have this set of highly qualified conditions. Currently, it's about 400. We have a set of highly qualified variants. If you were at Tom's lecture, he explained that. He explained it very well. These are right now pathogenic and likely pathogenic variants from the ClinVar database. And Tom in his talk explained how we're going to grow that from that baseline set to a bigger set. And then we have this database lookup phenomenon. Now, it's not just database lookup. That would be doable very rapidly. What we want to do is actually refresh the allele by zygosity frequency for all inheritance modes at all loci in the genome. That becomes computationally tough. That's a big exercise. Oh, and we need to do it for about 5 cents right? Because the total cost of the test has to be roughly $100, maybe $200. So we can't afford to do this with big iron. So that's where TileDB comes in, and ding. Are you happy now? Good. Okay, big question is, does it work? So first of all, does TileDB work? Does it actually solve this? So this is the famous M+1 problem, and it is that you hit the wall when your genome size reaches a critical size because it's super linear scaling, right? And it's real, trust me. We DBA'd the heck out of a MySQL database. We threw everything at it, and it didn't matter what you did. You could go on vacation because your query was going to take that long to execute. So instead, what we did is we set up this experiment. To my knowledge, this is the first time somebody's actually computed this and actually has an answer, which is staggering when you think about it. So what we've added is 4 million alleles to 125 million alleles, so one genome to 3,202. These are publicly available data sets, so it can be recapitulated by anybody. And when we ran that query and refreshed all those allele frequencies on TileDB, it cost 6.6 cents. They tell me they're going to get it to less than 5. I'm going to hold them to that. You are all witnesses. And that's on AWS S3. If you go with a conventional batching method, that's normally what people do, is they batch their data and they run it once a month or something. That's a solution. That costs $2.18. And alternatively, if you want to go the standard way, which is to buy a huge big cluster, Genome England tells me it costs them about $1 million a year and about $60 a query. So, tick box, that worked, that's good. Okay, now would this concept, newborn screening, work, or would we be plagued with false positives? Remember, the pre-test probability of a genetic disease in a healthy baby is probably going to be about 0.5%, right? 1 in 200. So you can't have a lot of false positives, otherwise it's a broken system. Doctors, parents are not going to put up with a test that has 50 false positives for 1 true positive. We think 1-to-1 is the right ratio. So a positive predictive value of sensitivity, whatever it is, 50%. So we put through its paces this entire gene set. Top line is the raw output, 0.75% false positive. That was actually pretty good. Tom was shocked. I was happy. But then we went in and did root cause analysis, because a few slides ago, here, you see these funky green lines? These are feedback loops. We wanted to build this system to be self-learning from the genomes it processes. So would root cause analysis or feedback loops actually work? And as you can see in this funnel diagram, it does. We had to remove only 9 variants. 9 variants, that's Irish math. Nobody laughed. I don't know, guys. Come on. Give me a break. And we got down to 0.26 positives. That's removing 3 genes, and we're probably going to keep one of those genes in. And Tom, you're just hearing this fresh, but they decided they're going to remove CD48 and CFI, which will get rid of quite a few of those remaining positives. So we're down now to an acceptable false positive rate, 0.26%. Because as I told you, we think we might have 0.5% true positive. Well, can we prove that out? Well, we now have lots and lots of decoded babies' genomes. And these babies have a high incidence, 33%, of genetic disease. So it was a matter of doing a retrospective analysis of those. And you can see the actual metrics there, 97% PPV, 99.4 NPV, 53.3% sensitivity. I know, Tom, they're slightly different than what I showed you. I looked again yesterday. Tom and I are working on this together. 99.9% specificity. This really works. Now, the sensitivity will get better with time, but already it's really good. The ones that were missing, which was 28 cases, it's because they're not in ClinVar. Let me just show you a case or two. Okay, this second one down is just, it helps you understand. Right, this is a little baby boy, and he has a stroke, and he has paralysis down one side of his body. Why? Because he has a very rare hemophilia, factor 13A deficiency. So he got rapid genome sequencing immediately upon being admitted with his intracranial hemorrhage. But it's too late. He's already had an intracranial hemorrhage. Had he been screened at birth, he would have gotten fresh frozen plasma or cryoprecipitate, and he wouldn't have had a brain bleed because it didn't happen at birth. Top one, baby with encephalopathy and seizures, same thing. They got a rapid genome, but it happened after they're already encephalopathic, and so there's brain damage. We can avoid that. It's just a matter of changing the diet. The same with the bottom one, biotin responsive basal ganglia disease. Same thing. And you can see there's time here. These are all babies who were diagnosed at 3, 4, 5 weeks. One of them, which I actually took off here, was diagnosed at 21 years of age. And it's just tragic when you think about it, that could have been avoided. So where are we at? And I'm nearly finished. We finished stage 1, that's feasibility. This is not yet public, okay? This is all secret stuff. It's not public. Did you hear that? So we're going to go public with this, we think next month. And then we move into scaling it. We want to scale it worldwide. You all are invited to join our consortium. We're building this consortium. We have technology companies, we have pharmaceutical companies, we've got academics involved. We really want to get this to become like diagnostic genome sequencing now is, which is starting to be thought of as a new standard of care. So I'm going to finish there. Adeo lumen ab amicis auxilium says, to God for creativity and to friends for help. This is the essence of multidisciplinary team-based research. These are the key contributors currently. Alexion Pharmaceuticals have paid an awful lot of the bills and contributed an awful lot of the intellectual horsepower. Illumina, obviously providing sequencing technology and informatics support. TileDB, providing our data management system. Genomenon, curating the variants for our system. And Fabric, helping with interpretation. And those are most of the people who are working on this. Thank you very much.
Excellent. Okay, thank you guys, and thank you for your patience. Big thanks to Dr. Kingsmore for the introduction, of course, to the mention to TileDB. I'm going to spend five minutes so that we spend some time for questions. I'm just going to give you an overview of TileDB, what the real magic is, and what makes all the work that we're doing with Rady and with Dr. Kingsmore very, very fast. All good? Excellent. Okay, I'm going to give you an overview of who we are before I get into some details. So TileDB is a research project that I had started when I was at Intel and MIT back in 2014 to 2017. It has deep roots in high-performance computing because of Intel, databases because of the group I was working with at MIT, and data science because of all the interactions that we had with a lot of scientists at the time in the area. We're well capitalized. We have raised VC money. We're over 45 members distributed across the globe, and we have a lot of traction across multiple different verticals. Genomics, and specifically population genomics, is the very first one that we started since my MIT days, and this is one of the most visible works that we're doing here. Okay, so here's the general problem that definitely applies to genomics, but spans way beyond it. We have talked to hundreds of organizations, and the story is the same. When the data goes beyond tables and the queries go beyond SQL, it's the abyss, right? For tables in SQL, we have perhaps 1,000 different databases and data warehouses, but it's very rare the case where an organization has only tabular data. And in the life sciences space, the tabular data actually is the small data. Okay, the bigger data is the genomic variants, single cell imaging, and so on and so forth. So it's not tables. And the problem is that there aren't sufficient data management systems for anything that is not a table. So what organizations resort to is storing the data in some custom formats and dumping the files into cloud buckets, and then trying to analyze this data with custom tools, right? Which more or less act like parsers. And this creates further problems when it comes to data sharing and metadata handling, because you need to know what each file corresponds to. So typically organizations build other databases on top of the actual data just to make sense of the data. And we have seen several organizations that either buy 10 different data systems that don't even speak to each other, or they build in-house, spending a lot of time, a lot of effort, a lot of money. And this prevents holistic governance and holistic search across all these assets, because the assets are very disconnected, and this makes the lives of scientists extremely difficult. And of course, this propagates to the organization itself, because the total cost of ownership becomes huge. So what is the solution? The solution we came up with is a data system that is universal. And it is universal in the sense that in a single system, very efficiently and very cost effectively, you can manage all types of data. And exactly because you can manage all this data, you can go way beyond exploration and analytics. You can do actual data science, machine learning, so more sophisticated tasks that you wouldn't be able to do by just parsing custom file formats. These are the 4 pillars of our database. First of all, you can store all the data in one place. And again, very efficiently, that's the second pillar. Anyone can claim that can unify data in a single platform. A file manager unifies all data. You know, it's files, whether it is an image or a VCF file, it's a file. The challenge is to be able to do so extremely efficiently, because performance is going to translate to low cost. That's exactly the challenge here. The third pillar is that you can do analytics, machine learning, and data science. And finally, exactly because you have all the assets in a single place, you can govern the data holistically. So you can have access controls, you can log everything, the observability is much more complete. So this is the secret sauce. I'm not going to get into too many technical details. I can discuss with you later, but everything boils down to the actual data structure we're using internally in order to store all this data. It's the multidimensional array. So we depart from tables, we depart from key values, documents, files. We store all the data in this mathematical form, and this comes in 2 flavors, dense and sparse. You can think of a dense array as an image, or vice versa, an image as a dense array, where every cell is a pixel and it has a value. But when it comes, for example, to genomic variants, you need to think in a sparse way. You can have the sample ID, you can have the contig, and you can have the genomic position in the contig, and every variant is a non-empty cell in a vast domain. So all the sophistication is built around this data structure when it comes to indexing, when it comes to fast operations, cloud native operations. It's all about this data structure. So for those interested, array subsume tables. So if you do have tabular data sets, just know, I'm not going to get again into the details, just know that there are a lot of creative ways to model extremely efficiently a tabular application with arrays. And you can go either with sparse or with dense, depending on what you want to do and what kind of query workloads you have. So you're not missing out on tables. Tables is just one of the applications that TileDB is capturing. So this is a very small subset of what we do. We have a use case for every single one of those. You can see, of course, population genomics there in single cell, as well as imaging. That could be very relevant to what you guys are doing. But of course, we're going beyond that. We have graphs, video, key values, and so on and so forth, and even flat files. So specifically for population genomics, I would like to tell you a little bit about how we model genomic variants. I mentioned it a little bit before, but now you can see it visually. Think of a population data set, so a collection of samples, as a 3-dimensional array. One dimension is the contig, one is the position, and one is the sample. And every entry in a VCF file, in a single sample VCF file, becomes a non-empty cell. And exactly because in the VCF and GVCF world, we're dealing with ranges, not just specific positions, but position ranges. We do a little bit of magic in order to be able to reduce range intersection queries to hyperrectangle inclusion queries. And this works magically in TileDB. So this is pretty much what this shows. We have a detailed webinar where we explain online, you can find it online, where we explain exactly how this works. And this is the software stack in case, again, you are data engineers, you're DevOps engineers, and you would like to see how this works. At the very bottom is the file system where you're storing the data, typically a distributed file system like a cloud object store. At the very top, a lot of different language APIs, a lot of applications, a lot of tools that you are familiar with. We're not introducing different languages. You get to work within within your comfort. And then in the middle, we're handling everything that has to do with storage, management, and compute. We have two different offerings: TileDB Embedded, which is a C++ library. It's an embedded library. It's not a server, and it's open source. This is what is handling everything around data storage, data retrieval. And then TileDB Cloud is the commercial offering, which allows you to collaborate in the platform, do scale out compute, do all the access control, the governance, and so on and so forth. I'm going to skip through this quickly so that we can wrap up and have some questions. So TileDB Embedded offers superior performance. It's highly optimized, very well engineered. It offers rapid updates online. This is what Dr. Kingsmore alluded to about the N+1 problem. We solve it extremely fast, exactly because of the architecture of our format. We offer extreme interoperability depending on what kind of environment you're comfortable with in terms of working with the data, and it is extremely, extremely optimized for the cloud. That effectively means that you can move your data and workloads to something which is more inexpensive in terms of managing resources. And TileDB Cloud is the service. This is where we manage the compute. You get to keep the data. You should be keeping the data in general, whatever solution you're going after. You can store your data in the TileDB format, store on S3, for example, and we take care of all the compute. So it is built to work anywhere. You can get it and install it in your own environment, or you can use our SaaS offering. It is completely serverless. You can do SQL queries, you can do user-defined functions, task graphs, and so on and so forth. You can spin up Jupyter notebooks if you're familiar with this. And we have several other capabilities that you might be interested in. The most important takeaway, and I will stop here, is that everything in TileDB is an array, even code, even notebooks, even dashboards, everything is an array. And therefore, we have a canonical way of sharing this data, logging this data, even monetizing this data. So last slides very quickly. The value proposition for population genomics is the cost and the performance. This shines truly, especially with the Rady use case. And we would like to put this to the test with your data sets. But we go a little bit beyond population genomics. We're working with Chan Zuckerberg Initiative as well as NanoString on single cell. So we normalize, again, the data under a single format, single API with interoperability across the tool chains like Surat, Bioconductor, and ScanPy. And finally, even for biomedical imaging, the images can be stored in TileDB. These are huge cohorts, huge collections of data that can be moved to the cloud, be compressed, and be much more economical than if you were using the supercomputing environments that certain organizations are using locally. So thank you very much. And both myself and Dr. Kingsmore are here for questions.
Just ask you to speak into the mic so our virtual attendees can hear. All right. You basically make the distinction between dense and sparse matrices, right?
Correct.
Does that mean that you have separate implementations for those? And if so, how do you decide which of these implementations you're going to pick?
Yeah, this is a great question. So there is a huge overlap of the code base between dense and sparse arrays. It changes when it comes, for example, to indexing, not so much on laying out the data. And this is the beauty of this. That's how we unified dense and sparse arrays under a single system. That was the big observation that I had when I was doing research. So huge overlap. There, it's not two different implementations. It's two different flavors, but not two different implementations. It's the same system. And when it comes to the decision, it really depends on the workload. Thankfully, for applications like population genomics, single cell, imaging, you know a priori. For example, for population genomics, you know it's a sparse array. And actually, we even offer the schema pre-optimized because we know it's going to be the same regardless of of how many VCF files you're ingesting into TileDB. The same goes with imaging. So for specific application domains, it's quite clear, and we provide scripts in order to create the arrays and ingest the data.
And when it's not clear?
Well, you do it empirically. You have to do it empirically. So, for example, for the sparsity, usually if the sparsity is above 80%, you convert into a sparse array. But it really depends. If you do some very highly optimized linear algebra, for example, it might make sense to store the data as dense, even if it's not very dense. It really depends. So what we have seen is that above 80% of sparsity, we convert to sparse arrays.
Really exciting discussion. And one talker from Pfizer had a question to Stephen here. So it's clearly, logically, this is real great progress. I'm wondering, as you scale use of this solution across multiple healthcare providers, how can you link into treatment and also potentially clinical trials? Because if you're in a pharma biotech companies, you might have a new treatment, for newborns, for particularly, say, for gene therapy, and how do you, how do you plug that together?
It's a great question. We're figuring it out. I wouldn't say we necessarily have, thought everything through yet, but we are developing a consortium of partners, and the idea really is that we want to make sure we've got a very diverse set, right? So we want every race, every ethnicity, and every ancestral group within races and ancestries to be adequately represented, so we have a true sense of allele frequency information, which currently we just don't have. UK Biobank is 98% or 97.4% white, right? So big issue. So we're thinking about where we set this up in terms of enrollment sites to help us with that. In terms of the pharmaceutical partner consortium that we're building, we want this to be pre-competitive, so that we are looking for as many partners as possible and basically trying to match, what are your diseases and genes of interest? What are your drugs that you're willing to tell us about that are already approved or about to be approved, so that we can build them into GTRX and so that we can qualify those genes and conditions for screening. And then obviously that needs to be highly dynamic, right? So that every year we're going to need to refresh that with newly approved products. And it's not just drugs, it's also devices and surgeries and diets. So that information is all going to increase with time.